All right, everyone, we're going to go ahead and get started. I want to welcome everyone today to the AAVSO webinar series. My name is Whitney Armentor, and I'm the Development Director for the AAVSO. It's great to see you all here today, and today we're going to hear a great presentation from Dr. Waalkes on Dwarf Starspots and transiting exoplanets. But before we dive in, I have a few announcements to make and a little bit of housekeeping to go through. First, a quick tour of Zoom webinar. If you take a look at the bottom of your Zoom window, you will see a few buttons. There's a chat box where we've all been introducing ourselves. There's also the CC or show captions button, which allows you to enable or disable Zoom's automatic closed captioning. And there's also a special button labeled Q&A. If you click on that Q&A button, you will have the option to submit questions for our instructors. You can submit as many questions as you like at any point during the presentation. Please don't worry, it won't interrupt the speaker. After the presentation, we'll have an extended Q&A where we'll try to answer as many of your questions as possible. Before we really get going, I'd like to take a moment to express our intense gratitude to our 2025 series sponsor. Voice Astro provides online astronomy education, observatory resources, and research experiences to students in schools to perform observations, conduct research, and publish results. Please check out their website at voice-astro.org to learn more about their offerings in astrometry, photometry, and spectroscopy. Support from our sponsors like Voice Astro and our donors make the work of the AAVSO possible. To support the AAVSO, please consider a donation by scanning the QR code on your screen or going to aavso.org. All your donations are tax deductible and support our mission of enabling anyone, anywhere to participate in scientific discovery through variable star astronomy now and for generations to come. And now it's my distinct pleasure to introduce Dr. William Waalkes. Dr. Will Waalkes acquired his PhD from the University of Colorado Boulder in 2023 and has continued studying transiting planets and stellar characterizations as a postdoctoral researcher at Dartmouth College. Later this year, he'll join the Solve-E research team at Max Planck Institute in Germany to work on the theory, simulation, and observation of magnetically active stellar photospheres. And with that, Dr. Waalkes, thank you so much.
Hi, Whitney. Thank you so much for the introduction. Just one sec. I'm trying to make sure that I can see my own video when I have the presentation up, and it went away. So I'm trying to get that back. I apologize. Okay. Oh, okay. I can't see myself, so this is a little weird for me now. Sorry, but if everyone else can see the screen, I am ready to start. So, hi, thank you for having me
Dr.
talk to
Will,
the.
I don't think we can see the screen. Sorry.
Oops. There we go. Okay, I couldn't see myself because I had not yet shared the screen. So here we are learning.
One last thing, we're on prisoner view. I don't know if you want to shift it over to another monitor or screen. Sorry
I
about that.
did, yeah. I told it to look at the other desktop. Okay, let's try
There
again.
you
How's
go.
that?
That's
Okay.
perfect.
Great. Sorry about that. You'd think 5 years in, Zoom would be like another hand, but no, it's still confusing. So, I'm here to talk to you all about active stars, the planets that transit them, and how stellar activity, in particular star spots, affects our ability to learn about planets and their atmospheres. Um, so, first of all, I am interested in atmospheres of sub-Neptune sized planets, so things that maybe could be like the Earth, or anything that's sort of Earth-like, whatever that means, to sort of Neptune-like. And so I want to understand the atmospheres of these planets. Those atmospheres can tell us things like what the likelihood of habitable conditions around other stars could be like, or what the formation pathways of those planets is. And so, or it just could be interesting because planets have atmospheres and they orbit other stars, and how are those different than ours? Um, so there are sun-like stars, G types, and I study stars that are smaller than that, so more like M stars. So, for example, an early M would be something like 4,000 Kelvin, and it would actually look redder. We call them red dwarfs. They're much smaller than the sun, and then even the smallest red dwarfs are tiny, that just a little bit larger than Jupiter, basically. Why are M dwarfs in particular an interesting star to study? Well, they're very cool, which means that there are shorter period temperate worlds. So you can have a planet around an M dwarf that's much closer to the star and still retain its atmosphere, unlike a similar situation around a sun-like star. Um, the smaller planet, or sorry, smaller star leads to larger transit signals. So a transit is the transit signal is the ratio of how large the planet is to the star. So smaller star, larger transit. And they have really long lifetimes. So this is very cool because planets can evolve through stages that we may never have even thought of. Their atmospheres can change in ways that we don't yet know how to predict because of how long the stellar lifetime is and how much time that provides for planetary evolution. And they usually have multiple small planets. So statistically, they will contain the types of planets where we can hope to observe planetary atmospheres. And they're also incredibly numerous. So again, sort of from the statistics argument, most planets with atmospheres that we can study orbit M dwarfs. But they're also not very cool. They flare a lot. They have an extremely high X-ray and ultraviolet flux, which evaporates planetary atmospheres. And they have very complex surfaces, which I think is scientifically interesting and motivates a lot of my work. But in the context of understanding planets, the complex surface really throws a wrench into things. So just to illustrate some of those things that I was just saying about M dwarfs, at the top we have an M star, a K star, which is between M and G, and then a G star like our sun. And so you can see this extent of the habitable zone being much closer to the star for the less massive stars. And the X-ray irradiance, however, is a lot greater. So 400 times X-ray irradiance. In this example, this is for an Earth-like planet around one of these stars. So 400 times X-ray irradiance is bad for your atmosphere and for biological processes generally. Um, so if we want to understand planets that orbit these types of stars, we have to have a really good understanding of the star itself. So there are all of these different forms of activity that stars engage in, and given that this is the variable star observer group, I'm sure that you are familiar with a little bit of this at least. So stars have star spots, or in this case, this is a diagram of the sun, so they have sunspots. There are these prominences, which if you observed or later looked at pictures from the eclipse from last year, or from actually almost exactly a year ago, uh, this was a very cool eclipse because we could see such a dramatic prominence on the sun when that was happening. And because the brightness of the solar disk gets blocked, the contrast goes down, and we can actually see the filaments of magnetically induced prominences and things that are, coming off of the stellar limb. There are coronal holes, so there's all this complexity with higher layers of stellar atmospheres. And there are things like flares, which are both tricky to deal with observationally and damaging to planetary atmospheres. Now, in particular, I'm going to talk about spots and how those affect planetary atmospheres. So, star spots are magnetically induced cool regions on the stellar surface. Um, there's a lot of active research going on to try to understand the physics of spots. Our current understanding is that it is formed when magnetic fields pass perpendicularly through the stellar surface. Gas density goes down because the magnetic pressure reduces gas pressure, pushes gas out of the region. And then if you have less convective motion, so less flux is coming to the surface because we've decreased the density of the material that transports that flux, that creates a dark patch. We're literally just seeing less light because the magnetic field inhibits the upwelling of that flux from deeper layers of the stellar surface. So that's basically how a spot forms and why it forms. We can never get this type of image of a spot for another star. This is a sunspot. This is an actual data image. And so unfortunately, we can't study any other stellar surface in the detail that we can study the sun. But of course, we can learn a lot of things about other stars from the detail that we get from the sun. So spots affect transmission spectroscopy of transiting planets. In this image, what we're seeing here on the y-axis is the amount of light which is passing through a planetary atmosphere. Oh, and in this example, the Earth. And so what this is saying is at these short wavelengths, ozone absorbs radiation, and so less light gets through the atmosphere. Okay, so I'm trying to set up a picture where we're imagining the star, the stellar photons passing through a planet's atmosphere, and then the planet that we observe actually has a different size at different wavelengths, depending on how much of the stellar photons are absorbed by the atmosphere at those wavelengths. So in other words, if, for example, here around this one micron point on the x-axis, this at least in this figure, this is not necessarily the most accurate science. This is just to display the molecular effects of our atmosphere. But right in this region, according to this figure, the stellar light passes all the way through the planet's atmosphere and is not absorbed. That means here the planet's radius will appear unchanged along these wavelengths. But then around here at this water wavelength, if water gets absorbed by the planetary atmosphere, then the planet's atmosphere will appear larger. So you're losing stellar light because it gets absorbed by that molecule. And therefore, at those wavelengths where that molecule absorbs, the planet looks bigger. Now, the complicating thing for planets and their atmospheres and spotted stars is that, for example, if we just have a planet here with a relatively smooth and unspotted stellar surface, but there's no atmosphere, then we just have some constant planet depth, meaning the measured depth in our transit. So a higher depth means larger planet, lower depth means smaller planet. And so this would just be constant with wavelength. There's no atmosphere, so it's just a solid sphere blocking light from another sphere. Now, if the planet has an atmosphere, then here on this y-axis, the planet depth is different. It has a pattern, it has a spectrum. And so here, this is a high resolution model, just showing if we actually observe the planet radius at infinite signal to noise, and we had this very high resolution, like the ability to study at a very high resolution, this is what one potential Earth-like atmosphere could look like in our data. It would appear larger, it would look like a spectrum because we are seeing the planet be larger at wavelengths where the atmosphere is absorbing stellar light. Now, this is the case with a simple unspotted stellar photosphere. If we have spots on the stellar photosphere, then those spots have a different spectrum than the average spectrum of the star. They have a different spectrum than the unspotted spectrum of the star. And because they are cooler, and because M dwarfs are already very cool stars, we can get molecular absorption in these regions of the stellar photosphere. And since we don't have the ability to spatially map a stellar surface like we can with the sun, effectively, we just look at a star, we see how bright it is over time, and we have to try to understand how much of that brightness is the brightness due to photosphere that is not spotted versus the contribution to the contribution from spotted sections. And so the spots add this effect because here in the background of the star, even though, again, we can't actually resolve images like this of other systems, the spots change our measurements of the planet because they change what the average background spectrum of the star is. And so if we assume there are no spots, but there are, then we have accidentally included the spectral features of those spots as an assumption of the planet, because we say, well, the star has no spots, so those features must be due to the planet. And that would be incorrect. And so the fact that spots do exist, the fact that their spectra do overlap with planetary spectra, for example, just to say it explicitly, these spots in M stars have water. They have water in them, which sounds bizarre, but it's water vapor. Not all molecules get blasted apart, even at, 3 or 4,000 Kelvin. So below about, yeah, roughly below 3,500 Kelvin, so around half the temperature of the sun, stellar atmospheres have water and other molecules. So because they have water, because we expect to detect water in planetary atmospheres, we must actually take account of both of these things at once. We cannot assume that our data is only planetary absorption or only spots. There's a relationship here that must be disentangled. So, how do we actually observe spots? Well, uh, the the original spot observation is stellar rotation. And so this graphic is from the Galileo project, and it puts together Galileo's drawings of spots on the sun. And you can actually turn them into a rotation diagram of the sun over time, just from his drawings, and they're pretty accurate. Unfortunately, he had to go blind to give us this data, but um, we can see that spots are the evidence of stellar rotation. So everything in the universe is moving, right? Nothing is just static, and every star is rotating. Some of them are rotating very, very slowly, but every star rotates. They generally rotate much faster when they're younger. They slow down over time. But the primary way that we can observe that rotation, or that we ever have observed that rotation, is through spots. The fact that spots are on the surface and the surface rotates means that over time, the face of the star that you're seeing is not the same. It changes brightness because it changes how much of it is covered in spots. And so the star gets brighter in time when it is less covered in spots, and it gets dimmer in time when it's more covered in spots. And so just observing the pattern, the periodic brightness change of a star, we can already begin to learn a lot about its spotted surface. So let's go forward from Galileo about 400 years and see uh, oh, shoot, there we go. What a more modern look at the solar surface and evolving spots would look like. So this is using recent data from DKIST, the new solar telescope that was built a few years ago. And I'm going to leave this slide up just for a moment, because if you look at it and you see it, you see it start over, you can start to notice a lot of the details going on with the changes of the spots, even in this short slice of rotation. So those spots they're evolving. Some of them are merging together. They're very dynamic, and that's exciting, and it's also intimidating, because that means, well, how do we try to understand this when how do we try to measure the characteristics of spots when it's already so complicated and so dynamic on the sun, and we're never going to have data that good of any other system. So trying to understand spots in the context of the extremely good data that we have for the sun is a challenge. And furthermore, we don't rather we know that other stars don't have spots similar to the location and structure of the sun. So there are other stars that are much more magnetically active. Their spotted surfaces are much different than the sun's. So one way that we can study spots is through spot crossings. So if a planet transits, so here in the lower right, this is a diagram showing a spotted star with a planetary transit in front of it. And if that planet transits a spot, then that should show up, or it will, if you have the correct signal to noise or sufficient signal to noise, it will show up in your transit light curve as a bump. And so that's happening because you cross over you're blocking a patch of the stellar surface, which is darker than the rest of the star. So the relative amount of light that the planet blocks is a lot less. So the bump goes up, the planet appears, at least for that those couple of minutes to be smaller. The planet looks smaller because we're always measuring size when we're looking at a transit light curve like this. We're seeing the amount of light blocked by the planet. So the planet appears smaller because it's blocking less light when it transits over a spot. And furthermore, a spot does not have the same spectrum at all wavelengths. It's not a black body. It is an object that has the characteristics of a stellar spectrum. And so that spot is brighter or dimmer at different wavelengths. So here, this is a shorter wavelength transit where that spot, and this is again just a simulation, this is not real data, but at this shorter wavelength, that spot is very dark. So when the planet transits over it, it appears to be blocking very little of the stellar light. But at longer wavelengths, the spot is not as dark. So when the planet transits it, it blocks more light relative to the shorter wavelength spot, and therefore the planet does not get doesn't that spike in the transit does not is not as high amplitude because that spot at longer wavelengths looks more like the surrounding stellar surface and is less of an aberration in the light curve. Now, another way that we can study spots is by looking at what's called a transmission light curve. So this spectrum of how large a planet is at different wavelengths. Um, Usually, we're taking a transmission spectrum to try to understand the planet's atmospheric absorption, but as I've already mentioned, this is a degenerate quantity with the spot spectra. And so if we, for example, had a planet like a brown dwarf even, which its atmosphere, because brown dwarfs are so high mass for a planet-like object, we wouldn't detect atmospheric absorption because basically the atmosphere is so tightly held around the planet that what's called the scale height is small, and it's the observed change in depth is very, very small, even though a brown dwarf is basically all atmosphere. It's dense and it's high gravity, so it's very difficult to observe that absorption. In a case like that, we could say, well, we know that our data is not showing features of a planetary atmosphere. Instead, what it is showing directly the features of the unocculted stellar surface. So, so in one way, we could hope to characterize star spots by, sorry, the Roomba just turned on inexplicably. So we can characterize star spots by studying something transiting the stellar surface and looking at the spectral characteristics of that transit depth with wavelength and determining if those characteristics of these bumps, for example, are due to spotted features not being transited, but that are in the untransited photosphere. So so now let's look at a specific case study of AU MIC. Now, this is a nearby star that is very bright and very active. It is 9.7 parsecs away, so that's quite close. It's 20 to 25 million years old. So one way to think of that is that this star was formed out of its parent nebula less than half of the time into the past as the dinosaurs went extinct. So when the dinosaurs went extinct, this star did not exist yet, which is crazy. This is very young. I mean, we usually think of things in astronomy as taking place on such long time scales that sort of the time scale of biology on Earth is very small compared to these astronomical time scales, which is often the case. But this star is still in the phase where it is contracting. It is still becoming a main sequence star. It's a very interesting target. It is covered in spots. And so we want to understand, does the planet around the star have an atmosphere? We expect that it does because it's so young that its atmosphere shouldn't have been evaporated yet, which is often what happens with planets. And we want to try to measure that atmosphere, in particular with Hubble data. So in order to actually be able to do that, we need to parameterize the stellar surface to understand how, right, okay, to understand how the spot temperature and coverage fraction or filling factor is how those quantities relate to the characteristics we measure about the planet. So just to return to this, what I mentioned about it being a very active star. So this plot here is the TESS rotation curve for AUMIC. And this is phase folded. So over many stellar rotations, the data has been folded together. And what we see here is the rotation curve in phase, which shows that the star rotates at about 5 days. So it does one full rotation every 5 days. And all of these vertical spikes are flares. And so the star is flaring constantly, and it's at all phases of its rotation, which means that it is spotted all around its surface. And it's again, the constant flaring is really a problem for a planetary atmosphere. But because this system is so young, we hope that our atmosphere is still on the planet, around the planet, and can be detected. So how do we begin to study the planets given the stellar activity? So we acquired ground-based data from a variety of different observatories. These vertical bars are showing spectral observations that we acquired. These red bars are the actual Hubble observation of the planet transit in two different visits. This happened back in 2021 and 2022. So there are two separate instances where Hubble looked at our system. And what I'm showing is ground-based data that we acquired to help study that Hubble data. And so all of these other marks, hey, all of these other marks are uh, rotation photometry measured from different wave bands in different locations that we've tried to combine to understand the multicolor rotation curve of this star. So to look at that another way, we observed in SDSS photometric bandpasses G prime, R prime, and I prime the rotation curve of the star, and we can see that the amplitude of that rotation decreases with wavelength. So this kind of goes back to something I had mentioned earlier, where the spot spectrum is not the same at all wavelengths. It is not just one uniform sort of characteristic. It has its own spectrum, and the ratio of that spectrum and the stellar spectrum determines what's called the contrast of the spot. So higher contrast means darker spot, and darker spots, or sorry, rather the higher contrast region of a spot is at shorter wavelengths, where the stellar and spot spectrum become more different. At longer wavelengths, in what's called the Rayleigh-Jeans limit, the spot spectrum and the photosphere are more similar, and so the contrast is lower, and the amplitude of variability is also less. So to think of it another way, you can imagine that four active rotating stars at a very blue bandpass, you would see a lot more variability than at a very red bandpass. If you took data from both these bandpasses, and at some red enough bandpass, that variability will go below the noise and it will appear not to be rotating. So we can take those measured amplitudes from a rotation curve, and we can parameterize that in terms of spot characteristics, which I put this equation up here not as a way to expect anyone to piece it apart, but just to indicate that we can take this rotation data, we can measure how much it's what the amplitude of that rotation is, and then we can parameterize that with the spot characteristics and say, well, if the spot is this temperature and your photosphere is this other temperature, what kind of spot coverage, how much of the surface needs to be covered in order to explain this amplitude? I hope this is making some sense. So, according to the ground-based data, AUMIC has an ambient photosphere temperature of around 4,000 Kelvin. Again, think of the sun's photosphere is almost 6,000, so it's a bit cooler than the sun. its spot temperatures are around 3,000 Kelvin, and it's something close to 50% covered in spots, at least according to the current understanding from our ground-based data. It could be more or less covered in spots, but yes, it is very highly covered in spots. To give you context, the sun at peak activity is about 0.2% covered in spots. So 40% is massive. Um, and that's why I sort of mentioned something earlier about how the sun is not exactly the spots on the sun are not quite how spots on other stars seem to work. So there's a limit to how much we can extend our understanding of the sun to other stars like this. So how do we actually measure a planetary atmosphere? Unfortunately, I can't show you full results from the Hubble data today, but I can show some of the products of the analysis that will show how things are complicated. So in this plot, the black lines in the background is our Hubble data. These transit light curves. This is just the white light curve, meaning the total bandpass integrated flux. So this is not looking at individual wavelengths of the transit, but just the total, the white, again, the white light or band integrated flux. And so this is showing one potential spot configuration that can help explain parts of this data. And this is not a statistical fit. This is more of an example plot. Obviously, the red lines, the model, are not perfectly overlapping with the data, the black lines. So it's not an excellent model, but it is good for explaining. And so on here, this is a cartoon of the stellar surface rotating, and within the time of our visit, which was about 11 hours, there's a significant change in the stellar surface. So we really need to um, improve our understanding of how spots are distributed around the surface, how large they are, what their temperature is, so that we can understand how these how they induce changes in the stellar rotation. So there's a lot of degeneracy here. This is I could add more spots to the star. I could take some star spots away from the model and still try to recreate this light curve. But yeah, any of those different sort of schemes are only an approximation to reality. We're still trying to understand what the true spot characteristics and the true sort of image of other spotted stars is. So here is the individual spectroscopic light curves from that band integrated light curve. And again, these are not sort of final models. They're not perfect, but just as a way to explain kind of how we do try to extract planetary information from multicolor stellar data. So this is trying to fit the transit depth and other characteristics of the planetary transit, uh, given that it is spotted and has a planetary atmosphere. Um, the current sort of status of this is that we're seeing a change in the planet radius with wavelength. So this plot on the right is showing the current sort of transmission spectrum. We are seeing that there are changes with wavelength in the planet radius, but to what extent those are due to the star or the planets is still uncertain. So it's an active problem, and one that what I'm hoping to address in my work, and to kind of bridge this back to how do we study stars? How do we better constrain spot characteristics? I want to talk about studying rotating stars with TESS. So TESS is the Transiting Exoplanet Survey Satellite. It launched in 2018 and has been observing basically the entire night sky. So initially, its focus was the 200,000 brightest and nearest stars, specifically just observing their brightness in month-long chunks to detect anything that might have some periodic change in brightness that could be due to a transiting planet. And so TESS has collected lots and lots of data. millions of stars at this point. And it has been a very cool project, I would say. It's a relatively inexpensive and simple telescope that has drastically updated our understanding of how many planets are in the galaxy, are orbiting nearby stars, and what types of stars are likely to have the planets that we want to study. So TESS is something that I've been working with for years now. I have been using ground-based resources to perform follow-up on different planets and try to find the best candidates for atmospheric characterization. Um, this one here, LHS 3844b, is not it's not a good candidate for characterization because it is just a barren rock. But we're going to talk about it for a moment, just because NASA prepared these great visualizations when this planet was discovered. And so this is the first full frame image of TESS. And in this little patch of this part of the detector, we found this planet LHS 3844. It orbits a very, very low mass star that was 0.15 solar masses, if you missed that. So um, it is 20% the size of the solar radius, 15% the size of the solar mass. So a very, very small star, very close planet, has about the orbit is 11 hours. So yeah, you can do the conversion of 365 days and 11 hours and figure out how much closer that planet is to its star than we are to the sun. And it is just a very hot rock. But I bring it up because, again, NASA prepared these nice visuals, and this was the first M-dwarf planet discovered by TESS, and I got to be part of that discovery, which was very fun. And so to highlight two other systems, this is TOI 122 and 237, just two low mass M-dwarf stars with planets orbiting them. And this is what I spent the first half of grad school basically doing, was observing these planets and trying to accurately measure how large they were. Um, Now, that was in the first few years of TESS, but since then, TESS has something called the Guest Investigator Program, and so there's a call for observations or for proposals each year where you can propose to use TESS and potentially use other resources as well to um, do some project that you're proposing. And with in collaboration with the AAVSO, I applied for and won a proposal to study rapidly rotating stars. So this is actually a project that I have yet to submit on the AAVSO campaign site, but it is something that I would like to humbly request the AAVSO's help. Well, actually, it's not even a humble request. You are collaborators. So in fact, this is now a research meeting, and and I should inform you on what you're on what you'd be observing. But so what the objective is to measure rotation of these rapidly rotating stars with the TESS bandpass, and then to acquire ground-based rotation measurements in bluer bandpasses from the community. And there are some other ground-based resources. It isn't only me and the AAVSO doing this. It's part of a larger collaboration with some researchers at CU Boulder in Colorado, and Dartmouth, and also the Kitt Peak National Observatory. So the idea is to combine all of these different resources from different locations and using different wavelengths and instruments from the ground to generate a multicolor picture of rapidly rotating stars, and ultimately try to accurately measure the temperature of the star spots. Um, Understanding the temperature of star spots is a lot easier and has a lot less degeneracy than trying to measure how much of the star is covered in them. But if we measure how hot or cool the spots are, and we have an understanding of that temperature for different types of stars, then we can really begin to constrain what the surface looks like, how those spots are distributed, how much of it is covered in spots. Um, and so this is just showing that multicolor rotation again. The idea would be to have multiple wave bands of rotation measurements for different stars in order to, uh, like I said, constrain spot temperatures. And so the targets that I chose for this, and that uh, anyone who's interested in helping with this research would be targeting as well. There's this handful, what is that, like 20, maybe 18 or something stars that are on very short rotation periods. So all of these have a rotation period less than 3 days. So they're very rapidly rotating. That's even faster than AUMIC, the star I was showing a case study on, which has a rotation period of 5 days. So these are even more rapidly rotating. And several of them, about half of them, have a rotation period of less than 1 day, which is very, very fast. I mean, I definitely have questions about these stars and how they fundamentally work, but this is also very interesting and I guess I think helpful for observing them because if you were to go out and observe one of these stars in a given night, you could capture a significant portion, if not all, of its rotation curve just in one night. So that's very helpful because part of the uncertainty involved in studying rotating stars is that you have to observe the star throughout several rotations before you can really constrain the period. And that can be very difficult, especially if you're on the ground and you don't have the ability of a space telescope to stare at something for more than 8 hours at a time, you know? So very short rotation period makes it a pretty interesting case, and hopefully a more observable one. And yes, you can see here their effective temperatures. These are all M stars, so they're all between roughly 25 and 3,300 Kelvin, and very small as well. Now, these types of stars will tend to be a little dimmer as well, but I am excited about the members and resources in the AAVSO because um, from my perspective, studying stars is very much a uh, we can do something with any data that we get. There is always a way to incorporate new observations into our understanding of the star to better flesh out the picture of what that star's spectrum is like, what its rotation is like, or other characteristics. Um, Looking at the names, none of these are stars that are colloquially known, but these are more or less their colloquial names. This isn't the TESS ID, which is a string of numbers, but you can go online and look up any of these stars and find information about them through some database. And taken together, I would hope to build a more comprehensive picture about what the surfaces of these stars are like, and hopefully a consistent picture since they're all very similar stellar type. I would like to build a consistent idea of what their spots are like, and therefore if stars of this type, of this temperature, of this rotation rate, can be treated as though their spots have a sort of uniform character between different stars. So trying to build up the statistical understanding of what spots are like, basically. And to show another kind of example of what the point of combining tests and AAVSO is, this is a plot from some earlier work I did with AUMIC, where I measured these rotation amplitudes. So the y-axis is rotation amplitude. I measured the rotation amplitudes in these three band passes. Oops, in these three different band passes. And in one visit, so Hubble looked at the star twice in two different instances, like I mentioned. And in one of them, we had ground-based data in three filters. But in the other visit, we had ground-based data in two filters. We did not have the third filter. Now, you can see the difference in the model results, which are these blue lines. That's just a high resolution model of what the variability would look like at different wavelengths. So you can see that here, these blue lines are, there's not too much spread because this redder bandpass, this is the closer to the TESS bandpass rotation measurement is much lower. It's less amplitude, and therefore the structure of the variability with wavelength has to accommodate that. Whereas, and so the shape of these models is strongly constrained by this particular point because it is very offset from the other points. Now, if we had only two of those band passes with similar measurements, and we didn't have that third band pass with a lower measurement, then those models are much less constrained. And in fact, the spot temperature that we measured in this case was much less constrained, had a much higher uncertainty than the spot temperature measured in this case. So adding a rotational amplitude measurement at any, I mean, there are preferred wavelengths, but in essence, adding it at any arbitrary wavelength gives us a more complete picture and allows us to better constrain what the variability of that star is across all wavelengths. So I'm going to take a breath to kind of bring this back around. The idea here is that I will be acquiring, or rather, actually, TESS has already acquired. I don't have the data yet, but TESS has acquired rotation measurements of almost all these targets, and that's just one bandpass of measurement. One bandpass is good, especially with these rapidly rotating stars. We can study the shape of that rotation curve over time. We'll get a pretty high signal to noise view of that shape because TESS is looking continuously at these stars. But one bandpass is simply not enough to understand the spectral characteristics of the system. And there's a lot of degeneracy. There's a lot left unknown if we make claims about spot characteristics or even just the stellar characteristics in general based on one bandpass. So the idea would be with AAVSO and with other ground-based observations, can we add bluer and maybe in some cases redder observations, but TESS is pretty red. So can we add bluer, optical measurements of these stellar rotation curves and then compare those measurements with the TESS bandpass measurement to see how different is the variability and because of that difference or lack thereof, what do we learn about the star spots? So I will leave this slide up with some closing thoughts on the things I talked about and the nice Galileo drawing, and I will happily take questions. Thank you very much.
Thank you, Dr. Waalkes. We have a good number of questions in the Q&A box. I can either read them to you or if you'd like to pop them open and go through them, but we have about 20 questions in the queue for you.
Sure. Okay. Yeah, I can. Okay, I've got it open. Let's see. Oh, it says some of them are already answered too. Oh, cool. Okay, so it's yeah, some of these like ppm. I apologize. Yeah, parts per million. There are lots of different flux measurements that people use in astronomy, and it can be confusing. But yeah, ppm is parts per million, so it's the same concept as percent is parts per hundred. So. Anyway, looking at the not answered questions. So what causes stars to slow down their rotation? Isn't this a violation of the law of the conservation of angular momentum? That's an excellent question, because if they simply slowed down without any exchange of momentum somewhere, then it would be a violation of the conservation of angular momentum. But stars are losing material. So they have coronal mass ejections, and that's I think the primary thing that comes to mind is coronal mass ejections. You are losing mass over time. So there's that. If you're actually ejecting energy, then there is an exchange of angular momentum. And furthermore, um, there is an internal gravity, sorry, not gravity. There's an internal, well, there's internal gravity, but there's a friction between the layers of the star. As the star is rotating, the different layers, all the material inside uh, there's this friction between the layers, and that's part of what causes magnetism. But it also means that there is a non-conserved characteristic of the rotation. So there is energy being lost because it's not a perfect, it's not a perfect system where all of the particles interact as ideal gases, for example. So it is losing angular momentum. And then there are also things like tidal effects. So large close-in planets can exchange angular momentum with the star as well and change its rotation and slow it down. This is the Earth's rotation is slowing down because of this interaction with the moon, in fact. So, um, okay. So this seems counterintuitive since spot should reduce the brightness of the star when added with the transit of the planet. I expect we should get a deeper transit. So yes, um, it's so I think this probably came up with the spot crossing, and so the idea is that what I was saying is when a planet, let me go back to the slide. Here we go. So the idea is, I was talking about how a planet transiting the spot makes this part of the transit light curve. It makes it induces a bump. And if, for example, that wasn't a spot, but it was just a hole, like a total lack of flux at that point on the stellar surface, then you could imagine this bump going all the way back up to the baseline level, because that's like saying the planet is blocking no flux. So in this case, when we're specifically talking about a planet transiting a spot, like the spot is on the transit chord, in that case, the planet over the spot causes the brightness to go up because the planet is blocking less light. So the brightness in the transit light curve goes up like this bump. However, it is the effect of the unocculted spots in the background is what causes transit depths to go down. And I didn't quite get into that because it's a little less intuitive. It would require, I think, a little more explanation and things. Maybe I just explained it enough to make it confusing, and I hope that's not the case. But basically, the unocculted spots, if they're not on the transit chord, they change the stellar spectrum in such a way that it increases the depth of this transit. But it doesn't increase it in a way that's like a bump like this. This is a spatially, this is related to the actual geometric overlap, right? But without that geometric overlap, if we're just talking about the integrated stellar spectrum, then yes, the spots cause the planet to look larger because it looks like the rest of the star is not quite as bright as in reality the photosphere would be. I hope that answered. So you do get a deeper transit if we're not talking about the spot occultation. We're just talking about the transit changing because of spots off the transit board. Um, So, which model atmosphere do you use for the spectral analysis of M dwarfs? Additionally, could you elaborate on the theoretical and computational methodology employed in constructing such model atmospheres? That's a really good question. I also that one might be a little beyond the scope of what this talk and what most attendees were prepared to learn about, because the theoretical and computational methodology for studying stars is it's complicated and it's in flux, and there's a lot of debate at the moment about what the sort of even fundamental assumptions should be. Um, so I guess to bring it up in one way, so in the intro, Whitney mentioned that I am moving to Germany to work on stellar theory. And so with that group, the process that we're undergoing is to synthesize new stellar spectra. Because right now, model atmospheres for stars and in general, just stellar models are really bad. Part of that is because in order to model a star and the spectrum of a star, we need to have a really good understanding of all of the atomic and molecular transitions that would be present. And our understanding of the atomic and molecular transitions that happen in a stellar environment is right now built upon line lists of molecular and atomic energy transitions that have not really been standardized or double checked or may not even have been measured and recorded in any kind of physical scenario close to what a stellar atmosphere is like. So we're relying on a lot of older and sort of less refined information about how molecules and atoms act. I mean, we understand on a fundamental, we understand the physics of atoms and molecules, but understanding the physics is different than actually having a measured line list for the energy level of all of their transitions. That's just kind of a big job to do with requiring lots, it depends on the context of what's the temperature and, pressure of your environment and all these things. So all of that to say, the yeah the current state of theory for generating the actual models of the stars, not the model that we compare to the data, but the model that we use to just describe the baseline. This is the model of a star. Those are very much I would say that they're in the process of being updated right now. So, but we're not quite yet at the point where where astronomers or physicists are particularly confident about the current stellar models. So, um, that's I hope I answered some aspects of your question, but that's yeah, the stellar modeling question, that could be a whole talk or a whole course on its own.
Hey, Will,
Um,
you mind if I jump in with the question?
sure.
Is
Yeah.
asked a lot, just to sort of avoid a couple of things. So people are wondering what filters in particular you're interested in. So most people are going to have Johnson Cousins. Fewer people are going to have SDSS, and they just kind of want to know if that's still
Oh,
useful.
sure. Oh, yeah. Yes. So yeah, I mentioned SDSS. This is what I had access to with the facilities I was using, but there are as many there are as many filter options as there are opinions on how to use them. And so generally my approach for this is whatever observations complement the test span pass. So we don't need a whole lot in the 700 to 1000 nanometer range. That's sort of near IR. That region is covered by tests. So basically, any filters that people are observing that are shorter than 7,000 nanometer, even shorter than 8,000, because the test bandpass is wide. So having sub measurements within that bandpass is still useful. But shorter wavelengths are particularly useful. So whether that's cousins or whatever filters you're using, and yeah, so those details I will iron out and I assume include that information with the campaign when I submit it online. But yeah, my top level answer is whatever data you can take, I can find a use for. If that helps. So what causes star? Oh wait, I already answered that. Sorry. I used both transited and non-transited spots in my spot model for AUMIC. That's a good question. So with the current work that I'm doing on AUMIC, it appears that there's a spot crossing. I'm uh, fairly confident that that is a real aspect of the data, but Hubble in particular is a very challenging instrument to use for this kind of work because Hubble has a lot of systematics. So the shape of the light curve has a lot of effects that are set by things that are just part of Hubble's instruments. Um, and yeah, I think that's the main point I was going to bring up about that. But because of these systematics, there can be basically if you set up your model with too many parameters, you can erase the spot characteristics. And so the transiting there is, I think, a spot crossing in some data I'm looking at, but it is still a challenging thing to measure and to understand because of all the other aspects of the data that need to be accounted for correctly. Um, uh, and then in general, I always have non-transited spots in the model because we know that there are spots on the star somewhere. So if we don't clearly see them on like within the light curve, within the transit, then they must be not on the transit chord. And so there are there are, in reality, probably both. There are probably spots on the transit cord and lots of spots not on the transit cord. So I include both of these possibilities in my analysis. Do we take into account the log G of the star when modeling the spots? Actually, I would say yes and no. So at this moment, I'm not taking into account because I'm not extremely concerned about how log G would affect measurements at the spectral resolution I'm dealing with, but it has been something that has been used in the recent past as a way of parameterizing spots as having a different log G than the rest of the star. That's not very physical. It's not very supported by the actual three-dimensional physical models of spots, but it is something that can be used as sort of an extra way to fit spots when you're not looking at a fully 3D scenario. So, I mean, usually we're not, if we're looking at a very simplistic version, then modeling log G can help to fit the spot characteristics. But that's a new thing that I've seen tried recently. But yeah, interesting question. Ground-based observation by amateurs, what observation data is being requested? Yeah, I kind of already talked about that a little bit, but just to say that what I'm hoping for most is rotation amplitudes, whether that is a single value that you measure from observing the scatter of a given star in a given night. That's one option. Or an actual rotation curve where you have measurements of how bright that star was over time, and you don't need absolute calibrations. This can all be done with just relative photometry. And yeah, I mean the core unit of observation that I think would be attainable would just be whatever for each person's setup and filters and preferences, however you would like to report an amplitude of variability or simply a measured light curve of the rotation of the star. Or, some of those things might sound like it's like, of course, I want to make sure that the requests are not too confusing or beyond the scope of what people's personal setups are like. But one thing I would say is that the first transiting planet was HD 209458b, was measured by Dave Charbonneau in Boulder, Colorado, in a parking lot with a 4 centimeter diameter telescope. And that was used to that observation, that paper became the justification for the Kepler Space Telescope. So if you think that your backyard setup or whatever is not good enough, that's incorrect, because as you already know, by virtue of being a member of the AAVSO, there is lots of science that we can do with the not massive facilities. So yeah, in terms of other specifics, that'll be something that I'll iron out more, and it'll be fleshed out in the campaign when I finally get around to submitting it. Do we expect flares for those M dwarfs in the target list? Yes. That is a good question. They probably will flare. The ability, or rather the observation of flares might not even be noticed, depending on the noise limits you're working with and the wavelength, or, the bandpass that you're working on. So there are plenty of times that a star is flaring, and in whatever bandpass, it simply isn't really noticeable. Flares are also a quick event. So if your exposure times are long, or you are just sort of you're observing something for maybe 20 minutes one night and 20 minutes the next night, even if the star is flaring a lot, you might not see it at all. So this could also be some interesting science that comes out of this collaboration, is whether or not we observe flares in different band passes for these targets. So flares and rotation can both be studied with these kind of multicolor rotations. Are the stars on the list available in the Swarthmore database? That's a great question. I'm pretty sure they all should be. So the Swarthmore database has observing information for it was, I don't know what it was originally built for, but my experience with it has all been for test objects. I think it includes things that are non-tests, but yeah, that database is definitely going to be useful. Okay, especially the short period ones. I'm not sure. I don't think I have a context of what happened before France Joseph's comment there. So if there's any clarification that comes up about that, what about the short period ones is my question. Um, in the meantime, would you be interested in infrared observations from private observatories from the ground? Yeah, I think that would be very interesting. Like I said, we have the TESS bandpass, but TESS is a very wide bandpass. It's 300 nanometers in width. So any kind of sub observations within that, or to be honest, even if you had basically a TESS bandpass setup from the ground and you use that, that would be fine because there's a time dependency in these observations as well. And TESS has already observed most of these targets. So if we get observations that overlap with TESS, but it happens much later than the TESS observation, that's still useful. Okay. Robert asks, with your test phase light curve AUMIC, you said the fact that it flares at all phases indicates there are spots all over its surface. Are there observational signatures of that, or are we assuming it based on the analogy to our sun? So that's a good question. A group of us are doing time series photometry and spectroscopy of stellar flares on M dwarfs. We're wondering if our data might be relevant to demonstrating the association of flares and star spots. Yes, I would say that without looking at your data or your project in detail right now, I would say you probably would be able to do very useful things associating flares and star spots. So the current paradigm that we work under with stars and star spots, or flares and spots, is that flares are associated with, rather, let me put it this way. We see a star flaring correlated with how spotted it is. So generally, we see a star flare when there are spots on the visible surface. So the flare could be, and I don't particularly study flares. I think about them in relation to spots, but I don't know offhand the physics of how flares work. But I think it's related to the like a prominence, which if we're looking sort of top down onto your stellar surface, then you wouldn't see a prominence. You're looking at the spot because the prominence is the like magnetic ribbon that's carrying hot gas out of like that region. But you see the prominence on the limb, and so the flare happens when the prominence, basically the magnetic energy is wound up enough that it bursts open and like there's a mini explosion. I mean, there's different types of flares. Again, I'm not a flare scientist, so hopefully that was a good enough explanation of them. But um, the idea is that flares are associated with spots. They originate from at least the same nearby region of the stellar surface, and so when we see flares, we expect, well, that at that time of the star's phase, it had to have had spots on that part of its surface. So yeah, there's definitely work to be done correlating spottedness with flaring. And yeah, good question. Do we know whether the M stars have a few very large sunspots versus many smaller spots? That's a good question. So generally, it is thought and understood based on our best kind of look at different stars down the main sequence at the moment. It's thought that as stars get smaller, the total fraction of their surface covered in spots goes up. So stars smaller than the sun should just generally be more spotted than the sun. Now, whether those have a few large spots or many smaller spots is a big open question right now. Um, I think in a case like AUMIC, where we're looking at a spottedness that's somewhere near half, right? It's at least 15% and maybe as much as 60% or so, and that value would also change throughout its magnetic cycle because the sun also goes through periods of being more and less spotted, more and less active. Um, so with a star like AUMIC that's so heavily spotted, I think that this is actually a case where it alone challenges the solar paradigm of spots, where instead of having a large number of small spots distributed around the surface, you have basically the whole surface is just a sort of like one interacting convective cell almost, where you just have huge regions of dark and light patches because this star is, like I said, it is collapsing onto the main sequence still. It is actively still becoming a star. And in this state, it's called a pre-main sequence star. And a pre-main sequence star is fully convective, which means that inside the star, the entire thing is one big convective zone. There's no radiative layer where things are so hot and the density goes down that you're just having radiation and no actual like upwelling of material, the convection. So the fully convective star like this must be heavily spotted because of because of the relationship between convection and magnetism and spots. That's a little bit beyond the scope, I think, of the science I presented in this talk, but this star in particular is just a very bizarre case. It's sort of an extreme version of spottedness that I think is probably as different from the sun as we can get. But that is just one case. There are many stars that are less spotted than AUMIC and more spotted than the sun. And so for those, there's very much an open question of, are there stars with few huge spots, or do they mostly have a lot of small spots like the sun? And it isn't the answer to that, which I don't have. The answer will depend on what type of star it is. So lower mass stars, again, they're more spotted. Those spots are probably larger. It's probably not just a ton of small spots. But yeah, these are active questions that people in astronomy are trying to figure, people in astronomy and astrophysics and theoretical physics are trying to figure out. Do dwarfs experience sunspot cycles similar to the sun's 11-year cycle? Oh yeah, definitely. These things, nothing in the universe is static. They are evolving. All stars are evolving all the time. I guess the closest thing to a static star would be a white dwarf, which is just cooling off until it is just a solid ball of nucleus. So yeah, they have evolving stellar surfaces. Part of what I'm hoping to see by studying these rapidly rotating stars in different bandpasses is the evolution of their surface. I would hope that in at least some cases we have enough data that we can look at how the stellar surface changed throughout its throughout several magnetic cycles and what the chromatic characteristic of that change is. So yeah, have I tried the Starry process Python package? Yeah, Starry is a really cool tool. I don't use it in my research because it is no longer being supported. And so basically it's going to just stop being able to be used with Python at some point, as things get updated. This code is not being, the Starry is not being updated anymore. So it's not a good choice for modern research, but it is a very good choice for playing around with spotted surfaces and actually trying to model a star with spots that evolve in time. So yeah, I do like that tool. There's another one called Spotter, Spotter. Spotter is similar to Starry, but it is it's more modern, and it is going to be actively maintained. And that is a tool that it's not, Spotter is designed more for visualizing than it is for actual research, because of some of the assumptions the model makes. But it does, I do like its ability to have spots change shape and to have complex shapes. Most of the models that I presented in this talk are the sort of simple first layer assumption of circular spots that don't have any special structure. There's no penumbra, it's just umbra. And when we're comparing to data in reality, those models are still good enough. I mean, more or less. But as you know, because we're in the era of James Webb now, our data is improving and the models must improve. Currently, there's work to be done to make sure that our stellar models can satisfy the requirements of modern data, basically. Am I asking for observations of the list of stars in my previous slide? Yeah, so that list that I showed, that's the target list for this collaboration. And of course that information will be more readily available as I work with the AAVSO to submit the project. George asks, how does limb darkening affect the models? That's a question I've George, my email I think probably went out with this talk, and that's a question that I think maybe is beyond the scope of this Q&A right now. But it is a good question, and it's a very important question. So feel free to reach out if you want to talk about it. Basically, limb darkening is in this picture here on the slide that's up. The star is darker toward the limb. Now that's something that is a lot more complicated than it seems, and especially once you have spots and you're trying to also have the precision to measure a planetary atmosphere, this limb darkening character of the star suddenly becomes much more important. So it's a thing that we need to understand. What aperture would I need to observe these stars? They seem rather dim and require scopes on the larger end. Wouldn't time series observation rather than one? Yeah, so from a sort of data acquisition side, these are dimmer stars. Not being on the AAVSO side of astronomy, I don't necessarily off the top of my head have a good idea of which of these stars would be observable under which, backyard type setups or amateur semi-professional setups. So some of this will be trial and error, and it'll be calculating exposure times for things, and then realizing maybe it's not feasible for that target. Some of these targets might not be observable by any of you necessarily. They're located at different places in the sky, observable at different times of year. So again, this is really we will happily work with what we can get, as with regards to data. What is being done to get better data on transition in stellar atmosphere? So if you mean like in reference to what I was saying about molecular and atomic transitions and the fact that we don't have very good comprehensive lists of those yet. So for one, it's a database problem where there are different databases with measurements from different experiments from the last century of, in literal chemistry lab experiments giving results of this is the energy level of these transitions and things. So part of it is just concatenating information from about a century of experimental data. Another part of it is the astronomical community or maybe the theorists or both needing to come to an agreement about which line lists are actually accurate, and if none of them are accurate enough, what do we do to build a new one? Because there's NIST, the National Institute for Standards and Testing. They have measurements, but they don't have all the types of measurements for everything that we need. So we use other databases to fill in information. And once you start combining molecular transition data from different databases, from different experiments done at different times, we're just suddenly in a mess. And so, yeah, it's a sort of like a scientific organization problem, I think. That's what I'd say about it right now. But yeah, the line list thing is being talked about a lot. We're trying to figure out the best way. To be honest, I think at some point just a whole new suite of experiments that are explicitly designed to measure these transitions in the astrophysical context is probably what needs to happen. But that sounds like a lot of work. And also for not astronomers, that's the chemists. They need to do that. So lower limit for useful signal to noise. That is a really good question. And hmm, I'm not sure I have a value that I could cite about that right now. I'll talk to Bert and get a better idea of what kind of SNR AAVSO astronomers have been able to get with their different setups. And again, I'm very much of the philosophy that any data is can be used somehow. Yeah, sometimes data sets are just bad or it was cloudy or whatever, there's not a lot you can do about those kinds of things. But even a noisy data set that doesn't show anything um, gives us a measure of the detection limit for whatever we're trying to do. So um, that's what I'd say about it right now. You also follow stars in the southern hemisphere. Yeah, so unfortunately, man, having a remote observatory in Chile is something that maybe if I had known that back when I proposed this project with Tess, maybe I would have changed the selection a little bit. But they're mostly northern hemisphere stars because I was designing a target list, which the A in AAVSO is American. So I was imagining people in the northern hemisphere, particularly the states, being able to observe things, and also the other facilities I'm using are U.S. based, except for one in South Africa. But that was the only telescope I had somewhere else, so I wasn't exactly prioritizing southern hemisphere targets. But France, that's good to know, and that's pretty cool that you can remote observe in Chile. Um, I can make a plasma at home and get a 1 nanometer spectroscope. Can I help get lines? I mean, I think at the level of line list measurements that we need, this is truly like a expensive lab equipment kind of need, but from a sort of personal data collection and spectroscopy standpoint, um, that sounds just like really cool for you to do is to make a plasma and measure its spectrum. I mean, that just sounds fun. I think you should do it. Um, but yeah, unfortunately, the solving that problem is much more up to like massive lab facilities and inter-institutional collaboration to organize that kind of update to the line lists. Um, so okay, there's one more question, and then I see there's sort of two more questions. There's one big one before that. The would amateur spectroscopy be a value? I'm going to say yes. I This is another one of those things that I would need to get a better idea of what that those spectra or that spectroscopy would look like what kind of wavelengths and resolution and things, but I'm going to say yes. Amateur spectroscopy would be useful. If for no other reason, then we can look at these spectra and compare to higher resolution spectra from other instruments and see, or even just for yourself, what what kind of information you were able to get from your homebrew spectral setup. So yeah, and then wouldn't the luminosity of a star with a bunch of smaller spots appear more noisy than the luminosity of the same star with a few huge spots, even if the total area of sunspots are the same in these situations? So, well, the total luminosity, I mean, there's part of this question which is about noise, and so if we're just measuring a value of luminosity, the noise is dependent on what the total brightness is and what your instrument is. But if we're talking about, for example, like the signal to noise that you could get in a rotation curve, if we're comparing one star with lots of small spots versus few large spots, the signal to noise of the actual observations, like of an individual observation, shouldn't change. I mean, if we're talking about the same star, same distance, same instrument setup, we're just looking at lots of small spots versus a couple large spots, that your signal to noise shouldn't be any different in either case. But the ability for you to measure a significant, like make a significant measurement on a rotation amplitude actually does increase with fewer large spots. And it's basically think of randomly distributing a bunch of small spots around a sphere versus randomly distributing a couple of large spots. If you randomly distribute a bunch of small spots, you're probably going to, yeah, I mean, like you could create lots of different shaped light curves, and a lot of those are going to have a degeneracy in them such that you could even see no rotation, because if you have a bunch of spots evenly distributed in a symmetrical way, or not even evenly, but just more or less symmetrically distributed, that just dampens the rotation signal. But if you had a couple of large spots, it's going to be harder to I mean, it's less likely that they will be evenly distributed in some symmetric way, and so you are more likely to have an over and under densities of spots in large portions of the star, and that's what leads to a large rotation amplitude. So the amplitude of rotation of the star is related less to its total spot coverage and more to the clumpiness of the spots, if that makes sense. When can we expect the campaign announcement? Great question, George. Soon. Yes, it is high on my priority list. I did have a child a year ago and then moved to a new job, so things have been a little busy. But yeah, I am intending to get this out, in the next couple weeks.
All right, I think that wraps up all of our questions. Dr. Waalkes, thank you so much for taking this extra time to answer all these questions and for just
Oh,
such a
sure.
dynamic and interesting presentation. And thank you to everyone here today on the webinar for attending. Let's see, trying to move my slides. 1 second, y'all. My turn for technical difficulties. There we go. I just want to take a moment again to thank today's webinar sponsor, Boise Astro. They have sponsored our entire 2025 webinar series. Boise Astro provides online astronomy education, observatory resources, and research experiences to students and schools to perform observations, conduct research, and publish results. Please check out their website at boise-astro.org to learn more. As a reminder, registration is now open for next month's free webinar. This one's scheduled for May 3rd, 2025, and we're expecting an interesting time with Dr. Rob Zellum on how NASA and citizen scientists help avert disaster. You can learn more and find the registration link at our website at aavso.org/webinars, and I hope to see you all there. And with that, I wish you all a wonderful weekend, a great rest of your day, and we look forward to seeing you next month. And thank you again, Dr. Waalkes, for everything.